Good. We're recording. It's 9:41 a.m. Pacific Standard Time, October 22nd, 2025. I'm going to start sharing my screen and go through the syllabus and the schedule of classes. Here we go. Let's see. We are writing here, 27th of October. We started with uniform circular motion. Then we will continue. That's our second meeting for uniform circular motion. And okay, we're gonna have lab number 2. Let's not forget the report for lab number 1 was due on last Friday, right? Let's write that down. Just as a reminder. Report for lab 1 was due last Friday, October 24. I hope to have it corrected before our Wednesday meeting. And we're going to have lab number 2 on Wednesday. Let's see how is the schedule is going. We're working on chapter 5. Exam number 2 is going to be how many weeks? 2.5, right? 2 weeks and 2 days. We're writing here 1 week, 2 weeks, and 2 days. Chapters 3 to 5 for now, right? For now it's chapter 3 to 5. We're gonna lab 1 through whatever we managed to cover. Maybe 1 through 2. Let's see how it goes. And let's go to our uniform circular motion, okay? Uniform circular motion. What we want to do? We want to find the equations of motion for an object undergoing UCM. And I already introduced that to you. The first 2 equations of motion, right? Which are the position, the components of the position vector. Is rather straightforward. All you have to do is to verify, to make a drawing of your object undergoing uniform circular motion right in here. Okay. The x component of this vector position is going to be x cosine of theta. And the y component is going to be r cosine sine of theta. R cosine of theta, r sine of theta. Okay? And then, what else did I tell you? I told you about the definition of angle. The definition of angle is written there in our last equation. Here we are assuming that the object started. Here you go. That's the definition of angle. Is the arc length S divided by the radius of the circle. Here you go. The arc length is this length here that I'm talking about, divided by the length, divided by the radius of the circle. That's the definition of angle. The very definition of angle. If the object goes one full rotation, then it's going to be S, is going to be 2 pi r, right? 2 pi r divided by r ends up being equal to theta equal to 2 pi, which is 360 degrees. So it makes sense, this definition of angle. Arc angle divided by the radius of the circle. Now, because the particle is undergoing uniform circular motion, this means that its speed is constant. Because of that, we can write the arc lengths as S equal to Vt. Okay, uniform circular motion. That's what it means. So the speed is constant, right? And consequently, the arc length is going to be given as time goes by. The arc length is going to increase with V as a function of time. And now we can here write the above equation for the angle. I'm doing that because I'm going to plug this theta right in here, okay? I can here write this equation for the angle as being Vt over R. Vt over R. And replacing that, remember, what's known here, right? Just as a reminder. The following parameters, reminder. The following parameters are known. R, V, which is the speed. And that's it, R and V. Okay, R and V are the known parameters. And now the X and Y coordinates of the particle can be here written as Vt over R. Remember, I told you that theta is a function. What the heck's going on here? Let's try it again. Yeah, okay, good. And now, okay, here you go. And now we have this, our first set of equations. For the position, right? And again, what are you trying to find? We're trying to find the equations of motion. We still need 4 more equations of motion, 2 for the position, 2 for the velocity, 2 for the acceleration. Okay, we need 4 more equations of motion. If you are going to write that not in terms of the Cartesian coordinates, but in terms of the polar coordinates, we write down R as being constant and theta equal to Vt over R. That's what's going to be the polar coordinates. Now, what about the velocity? What about the velocity vector, right? Oh, we can also determine it by inspection of the particle undergoing UCM. Inspection, there you go, right in here. And I want more than that, right? Let's see here if I have it. Yeah, that's what I want. I want this illustration here with the velocity vector. Let's see if you have another one. Here you go. This is the velocity vector here. Okay. We have to identify the angles properly so you can solve our equation. We can come up with the equations of motion. The first thing that you have to realize is that, don't forget, the velocity vector, I'm going to put it here, is perpendicular to the position vector. That's the first thing that you have to realize. I don't need that. Right? This angle that you see right in here is 90 degrees. That's what you have to realize. Let me put the symbol for 90 degrees right in here. Ay, 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 ay. Here we go. And then we have to put a little dot there as well to emphasize this is a 90-degree angle. That's the symbol that we use to denote that this thing is a 90-degree angle. Okay? Once you know that, you can start figuring out. I'm gonna put it here. The x and y components of the velocity vector. Okay, so here you go. What did I do in the next slide here? I came up with this line parallel to the x-axis. I need this line parallel to x-axis to identify the proper angles here. So here you go. Since we have a little z here, right? What does this little z mean? It means that this angle here is going to be equal to this angle. Okay? Since this angle is 90 degrees, so this angle here is going to be 90 minus theta. And now we can project the x component and the y components. Okay? And notice that the x component of the velocity vector is to the left, which means that it's going to have a negative signal, negative sign, cosine of 90 minus theta, and sine of 90 minus theta. Let's write it down. Okay, so I guess I'm even going to copy that and put in the notes so you have a good reference to understand how all those derivations end up being. Okay, so here we go. Like that. Let's get everything. Like that. Even better. I'm not going to get this funny. Let me copy something different. Okay. Now it's in the way I like it. Here you go. Here you go. We can also determine, we can determine it by inspection. Okay. According to this drawing, we have here go the x and y components, the velocity components of my particle are going to be, let's see here, and okay, the way we do it, I need to do one more step here. Let me do one more step here. Definitely this x component is to the left, so we must have the negative sign. This v here is going to be a magnitude. It's going to be the speed, okay? And it's not a sine of theta, but it is a cosine, not yet, right? It's a cosine of 90 minus theta. $90 minus theta. That's what it is. Cosine of 90 minus theta. But cosine of 90 minus theta is sine of theta, right? The negative sign remains, and we get this result here, dt over r. Vy, we do something similar. We do something similar to the Vy, to the y component of the velocity vector. But instead of cosine, we're going to have a sine. Sine of 90 minus theta, which ends up being equal to cosine of theta. We must have a positive, oh, not a negative here. Not a negative here. It's gotta be a positive. Let me emphasize that, right? And, we substitute theta by what we found before. And let me here write the x and y components. Okay. Here you go. That's what the x and y components look like, should look like. And then you can test, test when you go home. When you go home, test the above two equations for angles in the second, third, and fourth quadrant. Okay. The above derivation, let me write something else too. The above derivation was done for the particle in the first quadrant of the circle. When you go home, test the above two equations for angles for the particle, right? For the particle in the second, third, and fourth quadrant. Okay, what do I mean about that? What if the particle is right in here in the second quadrant? What if the particle is right in here in the third quadrant? What if the particle is right here in the fourth quadrant? Does the equation still holds? Okay. I'm gonna tell you yes, it still holds, but I want you to do that on your own, so you can convince yourself that those derivations are correct. Okay. And now we have to talk. So we have 4 out of the 6 equations of the 6 equations of motion. Huh, strange. My computer is stuck here. Okay, good. Let's see. Oh my goodness. Can you still hear me, folks? Yeah, okay, good. So the problem must be my Microsoft Word is stuck here in this place. Oh, well. I think I'll have to force quit the thing. Word not responding. Bear with me until my computer decide what it's going to do. Okay, look, good. Let's see if it works now. No. Oh, well. I'm selecting too much stuff. I know what the problem is. Next time I will select less text. I selected the whole document. When I select the whole document, it's too much stuff for the Microsoft Word to handle, and then it gets stuck like that. Let's wait for the computer. Okay. Uh, oh, that's really frustrating. Let me pause the recording. Okay, good. There's no need to report. Okay, now let's just get this paragraph. Good. Line space single. Good. Now the difficult part. The difficult part now is to find the acceleration vector. The difficult part is to find the acceleration vector. Okay? It's going to have an x and y component just like before. And again, inspecting the illustration, we can find the x and y components of the acceleration vector. Okay, and going back here to my drawing, here you go. Velocity vector, velocity vector. Here you go. Let's see. No, not this one I want. I want to go back here. Oh yeah, right in here. That's the one. That's the one I want. Okay? Note that the centripetal acceleration vector is contrary to the position vector. That makes life much simpler for us. Okay? Because of that, the centripetal acceleration vector is going to have the same format of the position vector, with the difference of a negative sign, and the term that goes multiplying there, the cosine and the sine, is not going to be the distance, it's not going to be the radius of the circle, but it's going to be the magnitude of the centripetal acceleration. Okay? Make sense? Okay, I'm going to write that down here for you. Note, and I'm going to copy that too. So I'm going to, like that. Oops. Okay, so notice that the centripetal acceleration vector has a direction contrary to the position vector, right? Notice that the centripetal acceleration vector has a direction contrary to the position vector. Consequently, we can write something like that, you know? I'm going to write the initial step first. I'm going to need this one later on. Here we go. A vector, okay? It's not going to be equal. It's not going to be equal. It's going to be just proportional to the position vector, but let's not forget it's going to be proportional to the negative of the position vector. Okay? That's what that drawing is telling us. That's what that drawing is telling us. So when we consequently, since the position vector, right? The x component of the position vector is r, lowercase r, cosine of vt over r. And the y component of the position vector is r sine vt over r. Right? Consequently, the x position of the acceleration vector is going to be minus, here you go, let me just remove this one for now, okay? Minus this guy here, multiplied by a factor that's going to be the magnitude of our centripetal acceleration, okay? And you write the same for the y component of the centripetal acceleration. You're going to be a minus a CP time. Okay, and I'm going to emphasize, I'm going to boldface this term, you know, just to emphasize that we still do not know what the value of this boldface term. We still do not know, we still do not know what is the value, right, of ACP, the centripetal acceleration. Okay, we still do not know. We'll find it now. We will find it now, comma, but we will find it now. Also by analysis, by inspection of the drawings, okay? See how it's important drawings in physics? So you can visualize your problem and come up with a simpler solution, okay? Okay, so we're gonna write it down. So, okay, our ACP in terms of the non-parameters V and R. V and R. However, we can use arguments of geometry to find this relation, right? And then I have to appeal again to the drawings. Here you go. Here you go. Here's velocity 1 vector, and here's velocity 2 vector, okay? Velocity 1, velocity 2. We're going to use, and we're going to use this drawing. Let me see. Here you go. V1, V2, R1, and R2, right? It's very important that we analyze this drawing. Okay, so what you have to note is an important relation between those four vectors, right? Between those four different vectors. And what is this important relation? This important relation is hidden in this drawing. Okay, so if I put my R1 V1 vector and V2 vector tail to tail, just like I did here, okay, just like I did here, I am going to find a very important relation between them and those other two vectors, R1 and R2. Okay, and let me, here you go. I'm going to separate them. Here you go. Let's say the angle between R1 and R2 is this angle theta. Not the position theta, but another, even better. I'm going to put theta prime, okay? So we can emphasize that this theta prime is different from that other angle theta. What happens is that this angle theta prime is going to be equal to this other angle here that makes that the vector v1 and v2 makes, okay? And it's possible to prove that rather easily. It's possible to prove that rather easily. So those are two, they make like two different triangles, okay? And those two triangles are similar to each other, okay? So here you go. How do we prove that? Well, just analyze it, just like we did before, okay? Just like we did before, this angle here is 90 degrees, right? Remember, this is a V2. This is V2, okay? And consequently, well, this the same angle that R2 rotates from R1 is going to be exactly the same angle that V2 rotates from V1, okay? And that's 90 degrees here. This one is going to be 90 minus theta prime, okay? And this angle here is going to be theta. It's going to be 90 minus theta. Sorry, this one will be 90 minus theta. Okay? And if you look carefully at that, you're going to find out that this one is going to be theta prime as well. Okay, so here you go. And that's the important, here you go. Relationship. Notice that V1 and V2 vectors, velocity vector, are two distinct points in the circle, form a triangle that's similar to the triangle formed by the R1 and R2 vectors. Let me copy that here. R1 and R2. R1 and R2 vectors. Here we go. One more student here to come in. The position vector 2 distinct points on the circle for the following reasons. Okay, for the following reasons. Here you go. Let me draw this. You're going to need that to understand. One, the angle between V1 and V2 is equal. Is equal to the angle between R1 and R2. And magnitude of R1 is equal to magnitude of R2. And magnitude of V1 is equal to magnitude of V2, right? Here follows from the fact that we have a circle. Here follows from the fact that we have a uniform circular motion. That's how we find that out. Similar triangles. Okay, here we go. Let me copy and paste that as well. It's there in my go. And again, that should be R prime. Let me theta prime, so you don't mix up with the. Here you go. Yeah, let me copy that. Like that. And what else? What else do we need? Remember, we're just so you don't lose the train of thought, right? We are trying to find out what's the relation of the centripetal acceleration with respect to V and R. And we need to go all through that to discover that, okay? And you're going to see why. Here you go. I'm going to put those two triangles next to each other, right? And let's not forget that what you see right in here is the final velocity V2 minus the initial velocity V1. Similarly, we have the final position R2 minus the initial position R1. And that's the similar triangle that I'm talking about. This angle here is equal to this angle. Because this length is equal to this length and this length is equal to this length, then those two triangles, they are similar to each other. Okay. In the next step, now we are going to really solve the value of the centripetal acceleration, okay? Here you go. Recall the ACP, right? It's our acceleration A. The acceleration has only a centripetal component. It has only a radial component. It doesn't have a tangential component. And the definition of acceleration is just delta V over delta T, right? Here you go. Delta V over delta T. V2 minus V1. Okay. But, you know, because those triangles are singular, okay, we can also state the following. We can say that delta V over V, okay, delta V over V, this length that you see here divided by this other length here, okay, is going to be S, S, the length of this arc, divided by V. Divided by V. Okay? And I'm saying that whenever delta V is small enough, make delta V is small enough, and then this delta V, the magnitude of this delta V is going to be, actually the approximation is going to be right in here. Okay? That's where the approximation is. That's where the approximation is going to be. No. Oh, wait a minute. No. Yeah, that's right. That's right. The approximation is going to be right in here. Okay? So what is going to be equality is going to be this one here is going to be the equality, delta R over R. Okay? Delta R over R. This is the equality. The approximation starts here. This equality applies because those two triangles are similar to each other. The approximation starts right in here because this delta R is going to be approximately equal to the arc lengths. Okay, to the arc lengths of the circle that the particle describes. Okay. And the smaller the delta R, the closer it is, it will be to S. S is going to be slightly greater than that, but if you shrink it, this angle, between R1 and R2, make it small enough, then we can apply this approximation. Finally, recall that S can be here written as V delta T, right? And that's supposed to be not S over R, but S over T, but S over R. Okay, S over R. Like that. So now we are at the point that we can finally get the centripetal acceleration. Okay? We are going to use, which equation are we going to use? We are going to use this equation right in here. That's the equation we are going to use. Okay. What else I'm going to do? I'm going to isolate this delta V. Okay? I'm going to isolate this delta V and pass the V to the other side. Here you go. V delta T becomes V squared delta T. Like that. Okay? And then we do something else. We divide both sides by delta T. We divide both sides by delta T. When we do that, here you go. The left side divided by delta T, right side divided by delta T. What do you have? When we do that, this term here is going to be our acceleration. Okay, that's going to be our acceleration, which, by the way, is a centripetal acceleration only. There is no tangential component to this acceleration. The delta T terms cancel out, right? So let's cancel out. Now, we go cancel and cancel. And look what we have. We finally have that making delta T, here you go, making delta T small enough, making delta T infinitely small, comma, the approximation becomes an equality. And the centripetal acceleration, the magnitude, right? The magnitude of the centripetal acceleration can be written as, writing that. And that's how we derive the equation for the centripetal acceleration. We recognize that there are two similar triangles in there, one related to each other. We can come up with equations. Here you go. Here you go. That's the equation for the similarity of triangles. This angle here is equal to this angle. This side is the same as this side, and this side is the same as this side. Then we apply this approximation. Delta R is approximately equal to the arc length. In general, this arc length is always greater than delta R. However, if you make that angle here small enough, S tends to be equal to delta R. Okay, S is still equal to V delta T. Oh, this is not an approximation. This is an equality, by the way. because S is equal to delta V delta T, okay? We have this approximation. We solve for delta V, divide delta V by delta T. So when we do that, we are dividing both sides by delta T. Delta V over delta T is an acceleration. We get V squared over R. And now all my six equations of motion become, you know, okay, two equations for the position, two equations for the velocity, two equations for the acceleration. And here's the centripetal acceleration. X and Y components of the centripetal acceleration. (10:30). Let's go. Now that we derived that, we can start applying these results. Okay? Okay, so let me copy and paste what we have covered so far in chapter 5. Uniform circular motion, centripetal acceleration. Now we are going to look at the centripetal force. Okay, and then you're going to solve some problems with banked curves, satellites in circular orbit, apparent weightlessness, and artificial gravity, apparent weight, vertical circular motion as well. Like that. Here you go. I can also rewrite those equations. Let's see. That's in the Cartesian coordinate system, right? Of motion in the Cartesian coordinate system becomes okay in the polar coordinate system. Let me write down the define equations in the polar coordinate system becomes, okay, so the R component is going to be constant, right? The radius of the circle. But in vectorial format, let's put that in vectorial format. Here you go. Vector is going to be the radius of the circle in the unit direction of the radial vector, in the direction of the unit radial vector. Okay, the velocity vector is going to be the speed But now this speed is going to be, this velocity vector is going to be in the, oh, not here. Let's see what's going on. In the direction of the theta hat vector. And the final, this is, don't forget this is known, right? And my final vector, which is going to be this acceleration vector, is going to be v squared over r. And then we must have a negative here because this is the negative direction of the unit vector r, right? Let's not forget that for the Cartesian, I'm going to rewrite the Cartesian here. The Cartesian in a different way. The Cartesian, the vector position, the equations of motion in the Cartesian coordinate system, right? Cartesian coordinate system. Like that, you go. Oh, well. And here you go. I'm going to need that. R is going to be what? X in the X hat. Oh, in the X hat, right? Plus Y in the Y hat. And I don't need that. Here you go. Velocity. No, velocity vector. I'm going to reuse most of all those things that V. You're going to have a X component of V. You're going to have the Y component of V. Vx and Vy was spelled out there before. Okay, and finally, I'm going to reuse this one here. A. I'm going to put AX, right? Plus AY. And let's not forget that we are going to have a negative here. You know what? Don't put a negative sign, okay? Because AX and AY are given, or were given before. We already have a negative sign there in the AX. We already have a negative sign implicit right here. And we also have a negative sign implicit right here. Okay? All those components can be either negative or positive. And then compare that to the equations in the polar coordinate system. Okay, you go. Compare that with the equation with polar coordinate system. Note C. I'm going to emphasize here that there is no theta component for the acceleration. Only a radial component for the acceleration for this type of motion, okay? Note that in uniform circular motion, let's write that down. Note that for UCM, the acceleration vector has no theta component, or note that for UCM, let us do everything here, right? One, the position vector has no theta component, no component along the theta direction, no component along the theta direction. Two, the velocity vector has no component along the radial direction. And three, the acceleration vector has no component, along the theta direction. Or, right? I'm even going to go further than that. He go, oh, yeah, theta component of R, right? R component of V, and theta component of A. Unlike, unlike in the Cartesian coordinate system, where all three of the above vectors have a non-zero component, right? Non-zero component, non-zero component, non-zero component, non-zero component, blah, 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 right? Here you go. Zero, oops. Zero component here. Zero component here. Oops. And zero component here. Zero component here. I'm emphasizing that only. Now we can start talking about Newton's law of motion for uniform circular motion. Okay, so by the same token, what time is that? 2:40? 2:40, no, 10:40, right? Let me just give you this brief introduction. And, by the same token that we have a centripetal acceleration, we must also have a centripetal force. Remember F equal to ma? Okay? If the only acceleration in a particle under uniform circular motion is the centripetal acceleration, so it means that particle will be subjected to a centripetal force. If subjected only to a centripetal acceleration, the only force acting in this object will be a centripetal force. And Newton's law of motion becomes, centripetal force. But don't forget, this is for uniform circular motion only, right? If the motion were not uniform circular, let's see, I need to copy this one and paste elsewhere. Here you go. Like that. And now we can apply Newton's law to objects undergoing uniform circular motion. Okay? And let's do example 5 from the book. Here you go. Example 5 from the book. Let's see if I have an illustration here. Okay, it must be this one here. Okay, yeah, that's the one right in here. here you go. What we have here, we have a model plane undergoing uniform circular motion. So you have a guy here attached to your model plane. He has a string attached to the model plane, and he moving this airplane in a circle. Can you picture that? Okay. So here you go. That model airplane is attached to a string and undergoing uniform circular motion. The mass of the model airplane is almost 1 kilogram. The radius of this circle is 70 meters. The airplane moves in a single plane, right? Such as its weight counters its lift force in the wings. That's another force. That's another force. Find the tension in the string for the following speed. V1 equal to 19 meters per second, V2 equal to 38 meters per second. Okay? So here you go. By the same token, you have a centripetal acceleration. You're going to have also centripetal force. I can even superimpose. Let's see here. Oh yeah, here is another illustration of the same model plane, but looking in the sideways, not from the top, right? Here's the string attached. Here's the weight of the plane. And like I said before, for an airplane to stay airborne, it must have a lift that's applied to its wings. Okay? So the net force along the z-axis here is going to be 0. Lift would be equal to the weight. And the plane will be able to move a uniform circular motion. The centripetal force, by the way, is going to coincide with the tension in the string. Okay? Here you go. The centripetal force here. Let me put it coincide with the tension. No, not that. Let's see if I can get that right. Yeah, good. Is going to be equal, to the tension. Like that. Oh, gosh. Oh, messing up here. Okay, good. Now we got it. Okay. The tension in the string. Okay, solution, right? You must identify the forces, just like we did. Plane. And those forces are weight, lift, and tension. Centripetal force is not a force, okay? Well, let's say the centripetal force is maybe a summation of forces. That's what we should say, okay? Use Newton's second law of motion for uniform circular motion. And here we have tension plus lift plus weight equal to mass times acceleration. But the lift cancels out the weight. Cancels out the weight like that. the tension coincides with the centripetal force. Okay. And this acceleration is going to be the centripetal acceleration. Let's put it this way. Here you go. Nope. Like that. And the centripetal acceleration is mv v squared over r. Oh, and by the way, here is r hat, not, let me correct that, r hat. Let's not forget that it's in the negative direction of the r hat vector. R hat vector is always away from the center. Consequently, we want the magnitude of the tension for two different conditions, okay? We want the magnitude of, let me just write here the tension, and I'm gonna put a magnitude right here. When I put a magnitude, I can drop the negative, right? And this unit vector is 1, that's the magnitude. We want the tension for two different speeds, right? Speed 1 is 19 meters per second. The length is, the radius is 17 meters. The mass is 0.9 kilograms. We get around 19.11 newtons. I don't want this one here. Let me see if I can do better than that. Yeah, that's how I want it. And then the second one is faster, right? 38 meters is twice the other speed. And let's see what happens to the force. If the force is twice, if the speed is twice, what's gonna be the force, right? You have to think about that. The radius did not change, right? The radius did not change. The force is not gonna be twice, even though the speed is twice. The force is gonna be fourfold. Because why is that? Because the velocity is squared, okay? Because the velocity is squared. Okay. Note C that by doubling the speed, comma, the force is increased by doubling the speed and keeping the radius the same, comma, the force is increased by fourfold, not twice. This is because the force is directly proportional to the square of the speed. Okay? Any questions? We have 12 students here. Let me take a quick roll attendance just to see how we are doing. Okay, Eric, are you there? Eric Alcala, I can see. Are you there, Eric? Okay, good. Thank you. I just want to keep track who's coming, who's not coming, right? Because I need to drop those people who stopped coming. Format cell date. Now, Edith, Are you there, Edith? I see Edith here in the row. She's the first one who came in today. Here you go. Jawaida, are you there? Jawaida Ali. I don't see Jawaida. And Evelyn Ayala. I don't see Evelyn. Ben Bandoy. I see Ben. Are you there, Ben? Ben must be away from his computer. Melissa. I don't see Melissa. Who is iPhone, by the way? There is a
Professor Ben said that he's here. He's messaging in the chat.
oh, he's messaging me in the chat. Okay, so let's see. Oh, you're here. Okay, good. Ben Bandoy. Okay, thank you, Ben. Sometimes I don't check my chat right away. Thank you. And Cecilia is trying to come in. Let's see here. Melissa. I don't see Melissa. Miesha. Miesha, I believe she dropped. Miesha. Oh, that's okay. Later on, I see that. Queen Castaneda.
Here.
Thank you. Emily Serna. Emily. I don't see Emily. Cecilia Chavez.
Good morning. I'm here.
Thank you. Isabella Cisnero. I don't see Isabella in the list. Jacob Contreras. I don't see Jacob. Delisha. I don't see Delisha. Gabriela. I don't see Gabriela. Angelica Franco.
Here.
Thank you, Angelica. Princess.
Here.
Thank you. Carlo Gallardo. I don't see Carlo.
Oh, I'm here.
Oh, you're there? Okay, Carlo
Yeah.
Gallardo. Thank you, Carlo. Brandon Guerrero. I don't see Brandon. Arturo Lagunas. I don't see Arturo either. Let's see, Janie Maldonado. No. Isabel Medina. No, Isabel. Next, Kimberly Morales. I see
Here.
Thank you, Kimberly. Montserrat Morales.
I'm here.
Thank you. Arwa.
Yeah, I'm here.
Oh, thank you, Arwa. Catherine Pettis. I don't see Catherine Pettis. Nicolas Rivera. No, Nicolas. Elizabeth Saldanha.
Hi, I'm here.
Thank you, Elizabeth. Jason.
Hi, I'm here.
Thank you, Jason. Armand. I don't see Armand. Jenia Tapia. I don't see Jenia. Next, Juan Torres Arellano. I don't see Juan either. Let's see how many students we have. And we can go, oops. Oh. Zero. Okay, who was not called? We're supposed to have 14 students here.
Me, Trin Hernandez.
What's your last name?
Hernandez.
Fernandez. Oh, you're not listed here. Why is that? Did you just add it to the class?
I was added a little while ago, but I missed 2 classes because I
Okay.
wasn't able to make it.
Let's see, Fernandez. Okay, so spell, let's see. Let me put that here. Gotta check. Fernandez, right? That's the last name or first name? That's the last name, right?
Hernandez.
Yeah. And
It-
that's the last name, right?
yeah.
What if
It's Hernandez.
A?
But my first name is Trin.
Well, I'm confused here. Let's see. It's Hernandez, not Fernandez, right?
Yeah, Hernandez.
Okay.
Yeah.
And that's your last name. So what's your
Yes.
first name?
Trin. Trin.
TRI. Okay. Okay. Now I remember. Three Hernandez. Why I didn't have you here? Strange. Maybe it's in my other roster. Hernandez. Right in here. Let's see. Let me delete that. 12, 13, 14. Blah, 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 blah. Yeah, let me see. Lab. Yeah, Trin Hernandez. Right in here. I put you in my lab roster, but I didn't put you in my lecture roster. Okay.
Okay, gotcha.
Yeah, that's why. Okay, 12. Now do we have now 3? Okay, 13. Now there must be another student that I didn't call that I called. Oh yeah, this one here, Edith. Okay, now we have 14. That's good. Okay, so let's take our break, our quick break. Break. 10:58 a.m. to 11:13 a.m. Okay, let's see. Do we have a question here? When you have time, are you able to check my mail? Oh, okay, good. I'll check, Elizabeth. I didn't check email today, but I will. I'll check. Thank you for pointing that out. 10:58. Okay, so I see you in 15 minutes. Okay, I'm back here. We are recording. Let's share the screen.
Professor.
Let's see here. Okay, I checked your email. Stream. This is what. Okay, so let's go back here. We did one example. Okay, now we're going to do another example, also another example from the book.
Excuse me,
And
Professor.
yeah,
Can you check the private message I sent you?
Yeah, is that Edith? Yeah, I saw it. I sent you a message, right? I replied to you. Did you see it?
I don't think I got it.
Let me see. Let me see. Maybe I'm mixing you up with someone else. Let me check here. Yeah, that's right. I think I'm mixing one. Let's see. Yeah, that's right. Okay, so sorry, okay, you are Edith, right? That and Edith. Edith. Yeah, I gave you attendance, Edith. I guess that's what you want to know, right? But
Thank you.
huh?
Thank
Yeah,
you.
yeah, you can type it if you have any problem speaking. You can type it. That's okay. Okay, so let's go for our next example. That's also an example from the book. Okay, a car is exiting the freeway and negotiating an exit turn of radius 51 meters. What is its maximum safest speed for the following conditions, okay? And notice that we have here the coefficient of static friction. Coefficient of static friction for our dry weather. You can see there is more friction in dry weather than in ice weather, right? The coefficient of static friction is much lower when you have icy weather. And he's asking the maximum safest speed. That's an interesting type of problem because it applies to real life. Okay? And think about that. You're driving the freeway, right? Most of the exits of the freeway have a very sharp turn. And you gotta make sure that you slow down enough to negotiate the turn safely without losing control of your car. If you're going too fast, okay, you may not be able to make the turn. And we can explain that through physics. We can explain these problems through physics. Okay, let me show you a slide how this, let's see here, not this one, right in here. That's, that's the situation, right? The car came out from the freeway. Let's say the freeway is in this direction, right? He came this way and then start making negotiate the exit. The radius, you have the radius of the curve, the radius of the exit, and you want to make sure that you're not going to crash. The car is initially here, right? And later on it's here. Here you go. Here's the velocity vector. Here's the velocity vector. Okay. In order for the car to stay in this curve, there must be a centripetal force that will ensure that he will not slide away from the curve. Okay. And we have to identify what this centripetal force is. The centripetal force can be 1, 2, 3, or more forces, okay? So it is like a genetic type of force. That's what the centripetal force. And then you have to identify what are the specific forces that make up the centripetal force. That's how this problem works. Let's write it down, okay? When we talk let's see. Let's write it down. For the car to safely negotiate this exit, comma, it must be subjected to a centripetal force that will keep it in the curve. If the centripetal force is not large enough, then you will lose control of your car, okay? And one more thing, keep in mind that the centripetal force is not necessarily a single force, but it may be a summation of forces. Keep in mind the centripetal force is just, let's put it another way, is just a generic way of referring to one or more forces that are pointing towards the center of the circle, okay? One or more forces that are pointing towards, that are pointing in the, let's put it here, that are pointing in the radial direction. In the radial direction, either towards or towards the center of the circle or away from it. Okay, that's what the centripetal force is all about. When I talk about the centripetal force, it's not that a specific force that you must identify in the problem, but it's actually a generic summation of forces, okay? So that's what it is. So this, here you go. So this centripetal force is not necessarily a single force, but it may be a summation of forces. Keep that in mind, okay? And we are going to look into that, into this type of force. Okay, so here you go. Here's the car is supposed to undergo uniform circular motion, and you must find what would be the maximum speed that the car can get into this curve to safely negotiate it. That's what it is. Okay? Here is looking at the car from the top, right? But if you look at sideways, here you go. We have those forces being applied to the car. You have the weight that's always there. You have a normal. And then you have this centripetal force that you still do not know which force it is specifically. And I'm going to tell you soon which force that is. What is the force that's going to keep the car in the circle, in the stern? Think about that. Think about that, okay? So, and I'm going to write it down. Here you go. So the question is, what is, are the specific forces that make up the centripetal force, okay? That's the question that you have to ask. And I'm going to give you a hint. I'm going to give you a hint. Okay? Suppose there is no friction whatsoever, no frictional force whatsoever between the tire of the car and the pavement, right? Then I'm going to ask you a question. Will the car be able to negotiate the exit safely? Okay? That's what I want to think about. Suppose that there's some oil there in the exit. And by the way, I have been involved in an accident with my car because there was some oil in the freeway. That was not fun, believe me. And I was going very slowly. Okay, I was making a curve. I was negotiating a curve that was a very tight one, but it was one of those lousy days in which we have a very little rain, and the water that accumulates on the freeway floats the oil that some of the trucks spilled along the freeway. And at that very moment, I caught one of those patches of no frictional force whatsoever, and I lost control of my car. Okay. So just from this story that I tell you, you should already be able to figure out what one of those centripetal forces are. Okay. The answer is no, right? The answer is no. This tells us that the force of friction between the tires of your car and the pavement has something to do with the centripetal force. Okay? Okay, so let's take a look at the car right in here, right? If there is no friction whatsoever between the tires and the pavement, this car is gonna just fly straight. You know, just will fly straight. I'm gonna draw here for you. No friction between, if there is no friction between no friction between tires and pavement, comma, the car will move in a straight line. Okay, make sense? So here you go. If the car was initially here, just a little bit later on, no friction, right? He'll be right in here, right? And so on, right? Let me shorten this velocity vector here. Here you go. That's what's gonna happen to this car. And if the driver is not careful, cannot slow down, cannot stop the car, he may end up losing control of the car. Okay, so, okay, no friction. If there's no friction, here you go. If there is no friction between the tires and the pavement, the car will move in a straight line. That's what's going to happen. But if there is friction, okay? But if there is friction, then the car will be able to negotiate this curve. And I'm going to give you, here you go. Here's the force of friction. I am not going. Let's see. I'll do better than that. Size and position. No, not with this. Not size and position. Format shape. That's what I want. Right, here you go. So that's the little secret of this problem, okay? I'm gonna put it in a different color. And hide this. Oh, another one. Here you go. The force of friction between the tires and the pavement. V is the velocity vector. Here you go. I'm gonna put it here. Force of friction. Force of friction. That's the only one that can be helping the car. Now the question is, which force of friction is it? Is that the force of kinetic friction or the force of static friction? That's another question, right? That you gotta make. That you gotta make yourself. Maybe. Okay, that's the next question. Okay, so here you go. What are the specific forces that make up the centripetal force? Suppose there is no frictional force whatsoever between the tire of the car and the pavement. Will the car be able to negotiate the exit safely? The answer is no, a resounding no, right? Is a resounding no, right? This tells us that the force of friction between the tires of your car and the pavement has something to do with the centripetal force. Okay. Now that we identified the force of friction, now that we recognized, right? Recognized that the force of friction has something to do with the centripetal force, the next step is to find out which force of friction is helping you. Which force of friction, kinetic or static? Kinetic or static is helping you negotiate the curve. Okay. Okay. It's I know our first temptation would be is to assume we are tempting, here you go, we're tempting to conclude that the force of friction involved is the kinetic one, because the car is moving, right? Because the car is moving, you know. However, note that the car is moving along the tangential direction and not along the radial direction. Okay? Think about that. If we convert the motion of the car to the polar coordinate system, you know, if we convert the motion of the car towards the polar coordinate system, we know, that the car, that although the car is moving along the tangential direction, it is at rest with respect the radial direction. Do you see the difference here? And it is also the radial direction and the centripetal force, okay? And the centripetal force is also along the radial direction. Okay? Consequently, here you go. The frictional force we are talking about must be the static force of friction, since there is no motion along the radial direction. Along the radial direction, the car is at rest. I'm going to emphasize here, along the radial direction, the car is at rest, right? If the car were to negotiate, if the car were to negotiate the curve safely, its speed along the radial direction must be 0. Okay? So this force of friction that you see here is actually the force of static friction. That's the conclusion that you take. Okay? This force must be the force of the static friction. And the force of static friction has an interesting, right, behavior that we covered before. The force of static friction has a maximum value, can vary from 0 up to a certain other value. Okay? So if you have a force of static friction here, this centripetal force is going to be the force of the static friction. And by the way, this force is applied here at the tires, right? Let me change oh, not this one here. Oh, yay. Here you go. I'm gonna put it in red color. Here you go. Bring to front. Right in here. I'm gonna put it in red color. That's what the centripetal force is all about. In this specific problem, the centripetal force is made up only by the force of static friction. In other more complicated problems, we have other forces in there. Okay, so here you go. And let's not forget that this force of static friction has a minimum value of 0 and a maximum value given by that equation that you have seen before. Okay? That's what it takes to understand this problem. That's what it takes to understand this problem. Okay? We have to do all this investigation, all this careful investigation. Solution. When you're looking at this problem for the first time in your life, you wouldn't know, it wouldn't appear that is the force of static friction. But if you make this type of analysis, it becomes clearer. Okay? Okay, so identify the forces. We identify the force. We have the weight, the normal, and a centripetal force. And now we know that the centripetal force is made up of the force of static friction. Okay? Apply Newton's second law to the car. Net force is equal to ma. This equation is a vectorial equation that has two components, one along the y direction, the other along the x direction. Okay? Along the y direction, we have this relationship here, where normal is going to be minus the weight, right? What does it mean? It means that the magnitude of the normal is going to be equal to mg. And now we have to worry about the x component of this equation here. This force, centripetal force, has no vertical component whatsoever, just horizontal component, right? There is no acceleration along the y direction. No acceleration along the y. Here you go. Let's write that down. Here you go. Normal and weight do not. Let's do it in a better way. Here you go. The only force along the horizontal direction is the centripetal force, right? Centripetal force. So, so here you go. So we can write this equation like that. Here you go. I'm going to take out is equal to mass times centripetal acceleration, right? The only forces along the vertical direction are the normal and weight. In addition to that, the car is not accelerated along this direction. Consequently, we can write the following. N plus weight, right? The normal is along the positive direction, but the weight is along the negative direction. So I'm going to write it in a different way. Here you go. Instead of writing like a vector, now I'm going to write like a scalar, where the negative sign is already implicit in the terms. Okay? It's like that. Okay? And we can here write it. The normal is upwards, right? So we can emphasize the fact that the normal scalar is a positive, has a positive value. And we can emphasize the fact that the W scalar is negative, okay? Like that, okay? This, so now I'm going to, we are going to need that, by the way. We are going to need this equation. Let me, normal equal to mg. And I'm going to see why. We identify the centripetal force as being the force of static friction. Okay. So we are going to have the force of static friction equal to m times acceleration. Okay. We do know that the centripetal acceleration is mv squared over r. Okay, but we also know that the force of static friction has a range of values. It is anywhere between 0 and the coefficient of static friction times the normal. Now do you see why I calculate that normal there? Okay, times the normal. This is the maximum value of the force of static friction. But let's not forget that the force of static friction is also given by the mass times v squared over r, right? Let's not forget that. Consequently, this equality here can be placed right in here, okay? Can be placed right into our inequality, right in our equation for inequality. Okay, here you go. And now you can see, the mass is gonna always be the same. The radius is gonna always be the same. Okay? It is consequently, it is the velocity that can vary from 0 to a maximum value. Did you get the idea? Okay? Did you get the idea? So this inequation can be here written as v squared, right? Greater or equal than 0, less or equal than r divided by m. I'm passing the r and the m to the other side. Here too, right? I'm passing the r and the m to the other side. But because this ratio is being multiplied by 0, right? It doesn't, the left side of the equation continues to be 0. And now we finally, here you go, finally found that we have this maximum value for the square of the velocity. But there is more. I solved for the normal because we need the normal here in this equation. This is a problem that involves two equations. This is a problem that needs two equations to be solved. You have to solve those two equations simultaneously to get the solution of your problem. Okay? Note, see that the problem in the book didn't tell you what is the mass of the car. It told you only what is the radius of the curve and the coefficient of static friction under two different conditions, dry weather and nice weather. Okay? It doesn't have the mass, but that's not a problem. That's not a problem. Why that's not a problem? Because the normal, okay, the normal can be rewritten in terms of mg, and the mass disappear from our solution of our problem. Okay? So from this inequation, we can go to the next step of the problem, right? Cancel out the mass and recognize that the maximum value of the velocity is going to be given by R mu sub S G. Okay? Here's going to be the minimum. And the minimum, you can put that the minimum value of the velocity is going to be 0, right? We can say that. But it doesn't help us solving the problem. We don't want the minimum velocity. We want the maximum velocity, the square of the maximum velocity, right? So we don't need that. And now we have R, we have G, and we have mu sub S under two different circumstances. Let's solve for the maximum velocity now. Should be the square root. The square root right in here. Oh. Square root. And then just crank the numbers. Get your calculator or get your spreadsheet, right? Plug in the numbers there. So now dry road, for dry roads, we use that value for the coefficient of static friction. We get 21.8 meters per second. Subscript. For icy roads, in which is very difficult to drive, it's very unsafe to drive, right? I once almost lost control of my car in an icy road because the coefficient of static friction is very low. Imagine if the coefficient of static friction for ice were to be 0, right? You don't have any friction whatsoever. It's much lower speed, icy roads. That's how we solve this problem. And 51, you gotta put 51 here. Whatever value for the coefficient of static friction here we have 10, right? 10 meters per second square times meter square per second square. So coefficient of static friction has no unit whatsoever, right? So we can see that this problem is consistent in terms of units. In terms of dimensional analysis, the dimension of the final result matches the dimension of the right side of the equation matches what we should expect for the dimension of the velocity. Okay, so it's 11:55 right now. Let's take another break. Do you have any questions? 55 a.m. to 12:10 p.m. Okay. So we have two students here that need the link for the lab, right? Make sure you stay after hours once we finish here. I have office hours today, and I will dig the link for your group folder, okay? And make sure you keep those links in a safe place so you're not lost there, all right? So you can have access to your group folder. So I see you in 50 minutes. Let's share the screen. Let's take a look at the chapters, right? The sections of the chapter. There you go. Self-10 now. Okay. We did uniform circular motion, we did centripetal acceleration, we did centripetal force. Now, we're gonna do bucket curves. It's a very interesting type of situation, is one of the bucket curves here. Let me show you how here's a curve that's not banked. Okay, it's just flat surface. But I believe you have already seen this type of bucket curves in the exits of the freeway. Okay, it looks like something like that, banked. This curve is, banked towards the center of the curve. And if it's built properly, a banked curve is far safer than a regular flat curve. Okay, if built properly, and there's a reason for that. There's a reason for that. Okay. Okay. Okay, bucket curves are, oh, not this one. What's going on here? Okay, consider, what's going on here? Okay. I was freaking out here. What's happening? It's my computer. Okay, now I figure out what's the problem. Here you go. Okay, bucket curve. Bucket curve is a curve tilted towards its center. It's not a flat curve like before. So in order for you to understand the effects of a banked curve, let's do this thought experiment. Okay? Consider a banked curve tilted with an angle towards its center. Now it would be the first frame of my movie, right? Let me erase that. I'm going to erase that. Here's the banked curve. And that's the radius of the banked curve. The radius, the horizontal direction from the center of the curve, right in here. Okay. Now assume that there is an oil patch on this banked curve. Let's see, I don't want that. I want the other one. Here you go. So assume that there is a oil patch or ice on the road, right? Oil patch on the banked oil patch on the banked curve. And also assume that there is a car at rest. on this banked curve and on the exactly on the oil patch. So I'm gonna get my car here and I'm gonna put it on the bucket curve, and but on the top of that, this car is at rest, okay? On the top of that, this car is going to be at rest. Bring that to the front. What's the tendency of this car, okay? If the what's the tendency of this car if it's put here in this oil patch, you know? The tendency of this car is to move towards the center of the curve. Can you see that? Right? Is to move towards the center of the curve. Slide towards the center of the curve. That's one extreme of the situation. Now, suppose that you instead, now, you have a car that's moving very fast. And it encounters the oil patch. Okay? Car going very fast. Okay, I want to delete this one here. Now. Let's see what I want to do. Oh gosh, let's see. Here you go. Let's tell the story again, right? Here you go. We start with the banked curve here, right? And there's an oil patch on the bank curve. We place a car at rest on the top of this oil patch, and the car tends to move towards the center of the curve. I'll put it right here. Erase this one. And now we are going to do the other thought experiment. Okay, instead of the car being at rest, and I want to instead of the car being at rest, now the car is moving very fast. Okay. Instead of being at rest here, moving very fast. What is going to be the tendency of this car? Okay, the tendency of this car, whenever you go too fast through the oil patch, is going to be to move in a straight line, and as the car moves in a straight line, the distance from the center of the curve will increase. So it is as though the car is moving. It's going to slide away from the center of the curve. Okay, that's what's going to will slide. Okay, I need to erase this one. Car will slide away from the center of the curve. That's what you should expect, okay? And then we have everything else in between. Here you go. That's the situation for the banked curve, for the case of the car going too fast in the banked curve. Moving away from the center. He is at a point here at a given distance from the center. A little bit later on, it will be further away from the center, and so on, okay? Well, what that make us think? What that make us suspect? That make us suspect that if the car at rest slides towards the center, and if the car going too fast slides away from the center, that make us suspect that there is this right speed that the car will have that will allow it to negotiate the curve. There's the sweet spot, you know, this right speed, the sweet spot right speed in which the car will be able to negotiate the banked curve safely. And we can calculate that using physics, okay? The situation is like that. similar to that one before. Okay, we have a centripetal acceleration towards the center of the curve. Remember, the car is driving in a single plane. That's why the centripetal acceleration is in the horizontal direction, okay? Because the car is moving in circles in a single plane. It's not doing that. It's not, it's not being all over the place, but just in a single place. It just happens here in a banked curve. Okay, here are the forces that are being applied to the car. We have the weight, and we have the normal. Okay, normal, weight, and a resulting centripetal acceleration. This centripetal acceleration will have the same direction as the centripetal force. There is no other force there anymore because there is no friction here between the tires and the surface and the pavement because there is an oil patch here. Okay. So, and then there is one more important thing. Since there is no frictional force to ensure that the car stays along its path, then there must be some other force in there that will serve as a centripetal force. If you look very careful here in this normal force, let me repeat that for you. Here you go. Normal force and the weight, right? You are going to see that the normal force has a horizontal component that serves just like a centripetal force. Can you see that? Horizontal component of the normal force will allow the car to negotiate this banked curve safely. And the vertical component of the normal force will cancel out the weight of the car. Do you see that happening? Okay. And I can write down here example. Consider a banked curve of angle theta and radius r. Let's go back here to my. Consider a banked curve of angle theta and radius r. There is an oil patch on this banked curve that reduces the friction to 0. Find the magical speed that a car must have to safely negotiate this banked curve. Okay. So how to solve this problem? Illustrate the direction of the centripetal acceleration, which must be in the horizontal direction, not parallel to the surface of the banked curve, okay? Not parallel. Not parallel because the car is moving in a single plane. Even though it's in a banked curve, it stays in that same plane. Okay, it is as though as the center of rotation of the car were this point here, not this point. Okay, or this point here in the drawing. The center of rotation of the car. Next, identify the forces acting on the car. In this case, it's going to be only the weight and the normal. There is no friction because the oil patch on the surface of the curve. After identifying these forces, notice that the weight has only a vertical component, no horizontal component, right? The weight has no horizontal component whatsoever. After identifying this force, notice the following. One, let's put it this way. The weight has only a vertical component. B, the normal has both a vertical and horizontal component, has a vertical and horizontal components. Four, I need to, let's see here what's going on. Okay. For the vertical component of the normal must cancel the weight. Component of the normal must cancel the weight. Of the normal must cancel the weight. And the horizontal and its horizontal component will act as the centripetal force being applied to the car, since it is parallel to the centripetal acceleration. Now apply Newton's second law. Just like we did before, but now the situation is different, right? They go. Net force is equal to mass times acceleration. And the acceleration in this case is going to be a centripetal acceleration. Is a centripetal acceleration because the car has constant uniform velocity, right? It's the uniform circular motion that we're dealing with here. We have the horizontal component. And we have the vertical component. And I'm going to take away this arrow there. There you go. Make the notation simpler. Centripetal force along the x direction. Okay, and we have the y component. Y. The car is not accelerated along the y direction. Consequently, its acceleration is equal to 0, just like in the other case. Okay. What's next? You go. The weight has no horizontal component whatsoever. And the centripetal acceleration along the x direction is v squared over r. Let's take a look. Okay, we know this, we know r, right? But we do not know the magical speeds. Let's see. The weight along the y direction is going to be minus mg. The normal along the y direction is going to be magnitude let's see, where is that? Gotta go here. Normal cosine of theta. Let's make sure it's cosine. Let's take a look here at the drawing, right? Yeah, it's cosine because theta is this angle right here with the vertical. When theta is equal to 0, the normal coincides with the vertical, right? As we keep on increasing this angle, the normal, the angle of the normal with the vertical is going to have the same angle as the angle of inclination. Okay? So it's cosine of theta for the vertical one. Here is already like that. Here I can change to n sine of theta. Okay. Next step. Okay, this guy here goes away. The n cosine of theta is going to be equal to mg. Theta is known. We solve our equation for n from here. Don't forget theta is known. Here you go. Replace this relation for n in the above equation. Here you go. Next, we are not going to use the second equation again, okay? I even going to eliminate it to make things simpler here. Okay, I'm even going to erase this guy because we don't need that anymore, okay? In the next step, we have tangent of theta, mg tangent of theta. By the way, the m cancel out with the m, and the magical speed that it will allow the car to negotiate this banked curve safely is going to be given by Rg tangent of theta square root. You know, there are many speedways out there that has a banked curve, especially for NASDAQ cars. There you go, Rg tangent of theta. For numerical example, you know, check example 9 of the book. I'm not going to do the numerical example. And that's very handy to have something like that, because if you're racing those speedways and somehow oil get spilled over the banked curve, everybody else who comes behind, they know what would be the safe speed, the magical speed that allow them to negotiate that banked curve safely. And example 9 in the book has something like that, a numerical example. Okay. So here we go. Let's take a look here what we have covered, how we are advancing in this chapter. We are done with banked curves, 5.1, 2, 3, and 4. And now we need to look at satellites in circular orbit. It is 12:33. Let's see, we have almost 20 minutes left, right? So let's move on to the satellite in circular orbit. Artificial gravity. Okay, so the first thing that you have to remember is Newton's law of universal gravitation, okay? Now you have two masses, m1 and m2, that separated by a distance d from their center. The force between them is gonna give given by that. So let's take a look here. Okay, here you go, satellites in circular orbit, mass 1, mass 2, distance d, force of 2 applied to 1, force of 1 applied to 2. Okay? And so suppose that we have this very small mass orbiting a larger mass, which is the case of satellites orbiting the Earth, for instance. And let's assume that those orbits are circular. Let's assume that those orbits are circular, okay? It's possible to prove mathematically, okay? It's possible to prove mathematically that the above force allows for uniform circular motion and other types of motion as well, elliptic, parabolic, and hyperbolic. Okay, but we're not gonna cover those three. Those three are too complicated for the sake of this course. Okay, we're going to cover only the case in which the orbit is going to be circular. So let's go for an example. So here you go. Going back here to the illustration, okay? So the force of gravity here in this specific situation is going to be the centripetal force. It's gonna act like the centripetal force. So do you see the types of force that can be a centripetal force? The force of friction can be a centripetal force. The horizontal component of the normal can be a centripetal force, right? The force of friction in the case of a flat freeway. Okay, a flat road that has a curve. The tension in the string of a model plane can be served as a centripetal force as well. The horizontal component of the normal in a banked curve can serve as a centripetal force. Okay, and we didn't do this problem, but suppose that we didn't have oil patch there in that banked curve. Okay, if you didn't have an oil patch in that banked curve, now here you go, going back to the banked curve, right? Going back here to this banked curve. Suppose there is no oil patch in the road, then you'll be able to introduce a force of friction here at the tire of the car. And now both the horizontal component of the normal and the horizontal component of the force of friction will act as a centripetal force. Okay, we have all those possibilities. So here you go. So far, we have seen the following problems, right? Following examples. One, following examples for that uses a centripetal force. Centripetal force. One, the tension in the string of a model airplane. Acts as a centripetal force, comma. Let's see. In the case of a model airplane undergoing UCM, okay, the tension in the string attached to the airplane, acts as a centripetal force, right? Two, in the case of a car negotiating a horizontal curve, comma, the force of static friction acts as the centripetal force. Three, in the case of a car negotiating not horizontal curve, but a banked curve with an oil patch on the curve, comma, the horizontal component of the normal as the centripetal force, right? And we have one more that we didn't do. The next one, I'm going to write that down here, is the one that we didn't do. In the case of a car negotiating a banked curve without, right? I'm going to an oil patch on the curve. The horizontal component of the normal and the horizontal component of the normal and the force of static friction act as the centripetal force, and so on, right? And now we have this other case as well. Similarly, for a satellite moving around the Earth, okay, the gravitational force acts as the centripetal force. Okay? And that's what we're going to do now. See 5 different examples that use centripetal force. 5 different types of centripetal force, right? So consider the satellite orbiting the Earth under uniform circular motion, okay? The mass of the Earth is m, the mass and the satellite is the distance r from the center of the Earth. Find the satellite orbital speed. The only force applied to the satellite is the gravitational force. You don't need to know the mass of the satellite to solve this problem, by the way. You know the distance r, you know the mass of the Earth. Don't forget, the distance r is the distance from the center of the Earth, not the distance from the surface of the Earth. So how is that? How does it go back to our drawing here, right? And the situation is like that. Here you go. Here's what you see right in here is my free body diagram. There is only this force applied to the satellite. Only this force. So here you go. The centripetal force is equal to mass times centripetal acceleration. The centripetal force, let's put it this way here. Centripetal force is equal to the mass times the centripetal acceleration. But we also know that the centripetal acceleration is v squared over r. 7 minutes to go. Okay. The only force acting in the satellite is the force of gravity. Consequently, the centripetal force is going to be equal to the force of gravity. Okay, that was going to be what? Big G, m1, m2 over r squared. Oops, not r to the cube, r squared. Oh, gosh. Good, like that. Oh, by the way, is the mass of the satellite. Which one is the satellite, M1 or M2? Satellite is M2, M1. Okay, so that should be M1 here. That should be M1 here. Okay. Let's see. Consider satellite orbit there. The mass of the Earth is M2. And the satellite is a distance r from the center of the planet. By the way, can you hear me, folks? Just
Yes,
give me
Professor,
some.
we hear you.
Yeah. Okay, good. Thank you. So here you go. Radius r. Let me put italicized. And here is going to be M1, right? Note, see that the M1 is going to cancel out with the M1. And now we have this equation in which M1 cancels out with M1. And one of the R's is going to cancel out with the other R here on the right side. Right? And then we get this relationship. And we finally have that the velocity of the satellite is going to be equal to this square root right in here. Okay. Mass of the Earth divided by the radius, the distance from the Earth, from the center of the Earth. That's one problem that you're going to see. 446. Let's see, 4 more minutes to go. Let's see if we can do it, the other one. Okay, now we are going to apply this solution that we got here to a numerical value. Okay? So here we go. Let the altitude of a satellite from the surface of the sea, from the mean sea level, be 400 kilometers. By the way, that's the average height of the space station, okay? Of the International Space Station. That's considered low Earth orbit. Find the numerical value of the orbital speed of the satellite at this height. Just apply this formula, right? So, but we are going to apply this formula, slightly different formula. Remember, r is the distance of the satellite from the center of the Earth. So it's going to be the radius of the Earth plus the altitude of the satellite. And then we can go to Excel to calculate, or even your calculator, right? I prefer to use Excel to calculate this value. Let's see. We need the mass of the Earth. We need the radius of the Earth. Gotta be meters. Here gotta be in kilograms. We're gonna need the big G. Yeah, I have big G here, right? Let me copy that in another spreadsheet. I have big G in another spreadsheet. Let's see. The radius of the Earth. That's the mass of the Earth. And that's the radius of the Earth. Isn't that nice to have everything already written down for you? Here you go. Put M1 here. Bold face, center. M1, let me subscribe that. 2 more minutes to go, radius of the Earth. And now I want to know the velocity, the orbital velocity of this satellite. Those are, real life numbers, okay, that we are gonna get. Now I have to write down my equation. Is going to be equal square root, right? Big G times the mass of the Earth divided by the radius of the Earth plus the height of the satellite, which is 400,000 meters. Close. Yeah, I got it. And by the way, here's not M1, here's M2, right? I call the Earth as the second object. And by the way, let me put here the height as well. The height is meters. 1 more minute to go. I put 400,000 meters, which is 400 kilometers, right? And here you go. We got it. And we can keep on playing with those numbers to find out the orbital velocity of the satellite. So look, it's 7.6 kilometers per second. It's very fast. In 1 second, you fly 7 kilometers. That's how fast a satellite moves around the Earth. That's how fast the space station moves around the Earth. It's something like 26 times the velocity of the sound. Okay, in terms of Mach speed. Okay, is this divided by 0.3. 25, 20. Oh, why do I have? No, it's not 0.3. It's 300. 330, right? Oh, here you go. 23.24 Mach speed is hypersonic. We call this type of velocity hypersonic speed, okay? And for 12:50, okay, we finish this section. We didn't finish the chapter yet, but we've finished this section on. Let me see if you have anything else here. Oh, so odd. Huh. Wait a minute. Okay. We can do more problems, okay? We're going to do more examples next time. We're not over yet with this section, and there will be more stuff to cover in this chapter. And we can stop right now, right? And Trine and Elizabeth. Is Elizabeth there? You can stay around, and so I can provide you with the link, okay? I have office hours right now. And if you stay around, we'll continue talking. Otherwise, I see you the day after tomorrow. Okay? Bye-bye.
Thank you, Professor.
Thank you, Professor. Have a nice day.
You too. Huh, they left. Oh.